And we're back. Welcome back and happy Thursday. Today we'll be continuing on with our discussion of virtual memory, but before we begin, some administrative bits. The reading, please make sure you're keeping up with the reading. That's pages 389 through 425 in the main text, sections 10.1 through 10.6.4. Including today, there are 6 class meetings left. Written exam number 2 will be out Tuesday in our class period on the 17th of November at 9:30 in the morning. You will have 30 hours in which to complete it and hand it in electronically via the course Blackboard. The residence halls will be closing this Wednesday, the 25th. That's the day before Thanksgiving at 5 p.m. If you are physically on campus, please make sure you are paying attention to that key milestone. The last day of classes will be Thursday, the 3rd of December. Reading day will be the day thereafter, the 4th of December. Our scheduled final exam period will be the 10th of December in the block of time between 10:30 in the morning and 12:30 in the afternoon. During this time, we'll be doing project presentations for the final project. The last day of finals will be the next day, the 11th of December. And for us in this class, our final projects will be due at that day, the 11th of December at 8 p.m. Okay, so where we last left off, we talked about copy on write. And with copy on write, we have shared pages between a parent process and a child process. And when one process writes to one of its pages, it gets its own copy of that page. And this greatly speeds up the time it takes in order to create a child process. And in fact, it makes sense if you think about it. Why create another copy of a page if you're not yet writing to it? All right, so let's look at page replacement. Now, we've been talking about the free frame list, and the free frame list, we said, it has a list of all the available frames that are allocated to pages for your processes that are running. And of course, as you increase the degree of multi-programming, you could come to a scenario where you just physically run out of free frames. There are many uses for frames. The many different processes that run on your system that have their associated pages have to be loaded into frames. But also you have demand from the kernel. And the kernel is maintaining all sorts of buffers, all sorts of I/O, and things like that. And it also needs frames from the free frame list. And so a natural question then is, if you have all of these processes, both the kernel as well as your process programs processes that need frames for their pages, how much do you allocate to each one? Now, absolutely, can you run out? Yes, that scenario can happen. So what do you do? And so in this segment, we'll talk about page replacement. Essentially, if you're running low or run out of free frames, you're going to find some page in memory that's not really being used, and you're going to swap it out to the backing store. And so the algorithm that does this says you swap it out to free up the frame that it's occupying, and then you can reuse that frame for some other page and allocate it to a different process that needs a frame if there is not a frame available, or the frame resources that are available are very, very low. And so what do you do with that process whose page that you remove from its frame? You could either terminate it, you could swap it out, you could also replace the page. Now, of course, performance-wise, one of the things that you're concerned about is that there's a degradation in performance, because swapping means that you're going to send something to the disk, and if you're going to replace it later, that means you're going to read some page off disk and put it into a frame. Moreover, the same page can be brought into memory several times. If you get pushed out, you might be brought back in again the next time you make a reference to a page that's currently no longer loaded in a frame in memory. And so the page replacement algorithm itself is purposed with making this determination about what page to select to evict from its current frame loaded in memory. And so this idea of page replacement is purposed with preventing the over-allocation of memory. And what this over-allocation means is that you run out of available free frames to which you allocate pages. And so it does this by modifying this page fault service routine in the operating system kernel to include this idea of page replacement. So not only are you going to load pages in to frames from the free frame list that you allocate them from, but you're also going to replace existing pages that are currently in memory loaded into frames. And so this is accomplished by a dirty bit. And this dirty bit marks each page as to whether or not it's been modified. And this dirty bit is going to be used to reduce the overhead of page transfers. Only the pages that have been modified or written to in memory are going to be pushed out to disk, because the others, you don't really need to push them out to disk. You just replace them, and then the next time you need to load them, you just reload them. And so you can avoid the writing of every single page when you swap out, only limiting that writing to disk to those that absolutely need to, because you have to preserve that data that has been written to that page by the process. And so with this, the page replacement completes this dichotomy, this separation between this idea of the logical or virtual address space and the physical memory. And this allows you, this page replacement, to have a very large virtual memory that can be provided or backed by a much smaller physical memory. And so this diagram is in the book, and it shows the scenario of what happens when you have over allocation of your frames, of your memory. So here we have two processes, user one, and let me set my pen here. User one, you can imagine this is process P1, and user two down below, you can imagine that's process P2. And here we have the logical memory, we have the pages for process P1. And so if we look at the page table associated with process P1 and P2, we'll actually look at the scenario presented here, and this is also in the book. So we have a total of 4 pages, pages 0 through 3 for process P1, and likewise for process P2, we have a total of 4 pages from 0 to 3 in their number. And if we look at the page table, okay, well, page 0, we're going to index into slot 0 in the page table for process P1, and we see that page 0 is loaded into frame 3. So if we look into memory, we notice in memory we have a total of 8 frames labeled 0 through 7. So if we look in frame 3, we see the contents of page 0 from process P1. It has this H. And then likewise, we have page 1. Page 1, if we go to the first position in our page table for process P1, we see that it's loaded in frame 4. So here's frame 4, and that frame 4 has an instruction that we'll talk about a little bit later. Likewise, page 2 for process P1, page 2 is loaded in frame 5. We go to frame 5, there's our J, page 2, and then lastly, page 3, we go to entry 3 in that page table. We'll notice here that it's not filled in, it's empty. We look at the valid bit, it's set to I, which means it is currently not loaded into a frame in memory. But if we do look on our backing store or swap space, we see the contents of page 3 for process P1 is right here on our backing store. And so let's imagine then this M is some instruction or some function block or what have you. And for that page 1 that's loaded into frame 4 in memory, we have a load instruction and it has a reference to M. Now, when the paging hardware looks up frame 3, or page 3 rather, in our page table, it sees, oh, it's invalid, and it wants to bring that M into physical memory in a free frame. But there's a little bit of a problem here. There are no free frames. If we look at process P2, we see its pages, A, B, D, and E. They are all loaded. Let's see, 0, frame 0. That's in, page 0 is in frame 6. So there's frame 6. Okay, we have page 1. That's not loaded. And we look on our backing store and we see here, this is page 1 for process P2. It's in our swap space on our backing store. And so the invalid bit is set to I because it is not loaded. We look at page 2, process P2, D, that's 2, it's in frame 2. So here we see the contents of page 2 for process P2. And then lastly, page 3 That's in frame 7. Here we see in frame 7 the contents of page 3 for process P2. And so here we have page 1 for process P2, the contents B, it's not loaded. And we have page 3 for process P1, it's not loaded. It's in the backing store. And we also have in the first 2 pages, page 0 and 1, the monitor or the kernel. The monitor is another name for the kernel. And so here we see all of the frames in physical memory are occupied. And therefore, if we were to reference this load M instruction, we're going to look up this logical address in the entry for frame 3. We see that's invalid, and now we have to make a decision. Where are we going to put it? So because all of the frames in physical memory are over allocated, they're all full, we have to make a decision about evicting one of these existing pages from memory to free up that frame. And that's what the page replacement algorithm is purposed with doing, making that decision. And so for the basic page replacement, it's 4 basic steps. You look for the location of the desired page on disk, so you locate it in the swap space. You find a free frame. If there is a free frame on the free frame list, you just go ahead and use it. But if there's no free frame, then you use a page replacement algorithm to select what's called a victim frame. You're going to say, aha, I'm going to pick this one. And you take the victim frame and look at its contents, and you write the contents of that current victim frame in memory to disk if it's currently dirty, meaning that if it has been written already, because you want to preserve that information that has been written. So then you bring the desired page into the newly freed up frame, and then you update the page content as well as the frame tables to reflect that assignment of that page that was brought off of the backing store, off the swap space, into that newly freed up frame. And then you continue this process by restarting the instruction that caused this trap to the interrupt service routine to invoke all of this process, all of these procedures. Now, there are potentially, when you do this, you can have 2 page transfers for page faults. And these 2 page transfer for page faults come from the eviction of that victim page from that victim frame, and then the loading of that page from the swap space to the newly freed up frame. Now, of course, anytime you initiate transfers of frames to or from your swap partition on disk, that's going to increase the effective access time, or the EAT, because that IO slowdown is a lot longer in its time than just an in-memory access. So you want to minimize the number of times that you go to and from the swap area, because it's going to make your computation much slower, because you're going to wait longer whenever you have an access for memory. Okay, and so this schematic is in the book, and it's an illustration of the steps involved in doing this swapping, this page replacement selection. And so here on the left, we have the page table, with the first column being the frame number and the second column being the valid invalid bit. And so the first thing that happens is you select a victim page and you swap it out to your backing store or your swap space. And then the second step is you change that newly swapped out page in the page table to be invalid. So next, you swap in the desired page into that frame that you just swapped out of. It's now available to be allocated to a page. You swap it in, okay? And then after that, that last step is you take that particular frame and you write that entry for the page you just swapped in to that available frame. And then you set its valid invalid bit to valid to note that now those addresses can be accessed in memory because they are now available. And so the frame allocation algorithm is that part of the system that determines how many frames you're going to give to each process, because you don't just start with as you need them, because it's a little bit kludgy. You're going to keep getting page faults and page faults and page faults. And so there are two components involved: the frame allocation algorithm that determines how many frames you're going to give each process and which frames to replace. And then there's the page replacement algorithm. And what this page replacement algorithm strives to do is to have the lowest page fault rate, both on the first access for instructions in a page as well as subsequent accesses. So if you minimize that first access and subsequent accesses, you're going to make sure the effective access time is as small as possible, because you're not going to pay those slowdowns for the repeated reading and writing and reading and writing of pages to the swap area. All right. And so when you evaluate page replacement algorithms, you evaluate it by looking at the number of page faults it generates on a string of memory references. And so the string of memory references is called a reference string, and then you compute from the accesses on this reference string how many page faults you get. Now, of course, in doing that, you're going to go to your system afterwards and say, all right, well, how much time does a page fault really take? And you can actually calculate real numbers from this. And so a string is just page numbers, not the address in a process. It's just a bunch of page numbers. And a repeated access to the same page does not cause a page fault. Why? Because once you have a page fault, you pay that cost for the swapping in up front, and then you have regular memory access. And so a repeated access does not cause page faults, and the results that you get for the performance depends on the number of frames you have available. And so in the book, in all their examples, they have the following reference string, which are the page numbers associated with the virtual address space for a process. And so I'm not going to read that off. You can look at it in the book. But here is an example graph. In this graph, on the horizontal axis, we have the number of frames that you allocate to a process. And then on the vertical axis, we have the number of page faults. And what you can see here, it sort of asymptotically decreases. And as you increase the number of frames, we see that the number of page faults goes down. And that kind of makes sense, because if you allocate more frames to a process, more of the virtual instructions will already be associated with pages that are already loaded into frames, and therefore you're going to have fewer page faults over time, especially because of locality of reference as you execute instruction and then the next instruction and the next instruction and so forth. And so we see this general scheme, and let's look at one of our first of many different variations of page replacement algorithms. This is called first in, first out, or FIFO, and essentially it replaces a page or selects a victim based on which one arrived first. The first one that arrived is the first one that's going to be replaced when a new page reference occurs. And so we start out, we have our reference string here, and we start out with 7. Of course, the first 3 page faults, when you're allocating 3 frames in the beginning to each process, you can't avoid those first 3 because you have to fill up your initial frames allocated with the pages for your program or your process. And so here we have page 7, so we get a page fault. Okay, we have page 0, we get a page fault, and we load that into the next frame. And then we get a reference for page 1, we get a page fault. So now we get a reference for page 2. Okay, well, the first one in was page 7, so we're going to replace that one. And we write in a 2 in the place of 7. So then we get a page reference for 0. Well, 0 was already loaded, it's still there. So we don't pay any cost in terms of page fault. We don't count that. And then we get a reference for page 3. Well, the second one after 7 was 0. So we're going to select this page where the 0 reference was to replace. So we write down 3 here. And then we have 0 here as another reference. Well, 0 is just there, but it got kicked out when the reference to 3 came in. And so 0 is going to replace the 1, which was third. And so now we have a reference to 0, and it replaces that 1, okay? And then we have a reference to 4, and this FIFO continues. And each time when we do this, we count each one of these blue boxes represents a page fault because we're replacing a page in this FIFO order. And so if you count these up, it's a total of 15 page faults using this first in, first out page replacement selection approach. And so this can vary if you change the reference string. Now, if we change it to this, I won't do it out, you can actually get a different number of page faults. And so it would behoove you then to try a bunch of different strings and look at averages and things like that. But there are some cases where adding more frames can cause more page faults. And this is called Belady's anomaly. Now, it might seem non-intuitive, but if you think about what's happening, for example, what we happened here, we had 0 as a reference, and we didn't have a page replacement. Then when we had 3, we replaced the 0, and then we had 0 again, and we ended up swapping in the 0 again. And so Belady's anomaly has to do with the fact that if you have more frames and you have repeated access to a page span across time, you can end up getting more faults. And so one of the things we want to do is to track the age of the pages. And to do so, you can just use a FIFO queue. And so this is an illustration of Belady's anomaly. And what you can see here is if we, for that same page string that we had at the beginning, starting with a 7, if we increase the number of frames from 3 to 4, we actually increase the number of page faults. Okay, and so this was an interesting observation. And one of the things that was done to change this flaw in FIFO is that you want to consider this idea of this repeated access to a page, because if you evict a page, select it as a victim, and then you don't use it, and then next time you need to use it again, that repeated access can be the source of a high count for your page faults. And so increasing the number of frames does not help you, can lead to an increase in the number of page faults. And so one of the approaches you can do to make page replacement optimal, i.e. minimize the number of page faults, is to replace a page that you think won't be used for the longest period of time or won't be accessed for the longest period of time. But this is future thinking. It's hard to predict, because if you're going to access a page now, you're not sure sometime from now if you're going to access it again a number of times. But if you can do this longest period of time scheme, for this example, 9 page faults is optimal. And so how can you know this? Because you can't look into the future. Well, you can use the references that your algorithm performs in the past to do this. And so here we have a reference string, the same reference string, and now we're looking at our 7, we have a page fault, a 0, we have a page fault, 1, we have a page fault. And now when we get a 2, okay, well, we replace the 7, we have access to 0, well, we don't pay any cost. And now when we get the 3, instead of replacing in FIFO order, we say, oh, wait a minute, the 0 was accessed most recently. And if it was accessed most recently, we know that it's going to be used at some point again relatively soon. So instead of replacing the 0, I'm going to replace the 1. And we replace that, and then here we have the 0 access, and the 0 remains fixed. And so doing that, or considering this idea of which one will go unused, which page will be unused for the longest period of time, and replace that one first, you eliminate Belady's anomaly by making sure that pages that are accessed more frequently over time tend to stay in frames longer, i.e. they're not considered first for being replaced by the page replacement algorithm. And so this optimal approach is different from FIFO, and it minimizes the number of page faults and therefore making the effective access time as small as possible, which leads to better performance on your system. And so there's an algorithm that is a take on this longest access time, and this longest access time requires predicting in the future how much you think you'll be using a page for a particular set of processes. And so it's really hard to do this. And so what this LRU, least recently used, does, it makes the assumption that past knowledge is a good predictor of future behavior. And so with this least recently used, you replace a page that hasn't been used in the largest amount of time. And so if you're using something, a page 10 times referencing it, and then another one is being referenced one time in the past, then that one referenced one time is more likely to be selected as a victim than the one that's accessed more recently. And so least recently means how far into the past that page has been accessed. And so in implementing LRU page replacement algorithms, you're going to associate a time of last use with each page. And so you include a lot of different ways you can do this with a counter, timestamp, or what have you, but you associate a time of last use with each page. And so in that, and this schematic is in the book, we have our same reference string, and we say 7, okay, page fault, 0, page fault, 1, page fault. Now we've allocated all of our 3 many pages assigned to this process. So then when we say 2, okay, well, the most recently used was 1, the next most recently used was 0, and the least recently used was 7, so 7 is going to be replaced. So you replace the 7 with a 2, now you have 0, okay, that's used. Then you get a 3, and you're going to replace the 1. Because at this juncture, 1 was most recently used, 0, it was just accessed with this reference, and 2 was most recently used, and so it's going to replace the 1. It's the least recently used. And so we keep with this algorithm, and if we look at this, we have a total of 12 page faults. A page fault is represented, again, by each one of these blue rectangles that list all of the pages that are assigned to various slots. And so here we have 12 faults, and these 12 faults is better than FIFO, which had 16, but it's not optimal, which had 9. And so a generally good algorithm frequently used, this LRU, it's used in practice, but the next question is how you would implement this in your system, because it might require some specialized hardware. And so one of the approaches that people use to implement LRU is a counter. Every page entry has a counter, and every time the page is referenced to this entry, you copy a clock into this counter. And therefore, when a page needs to be replaced, you look at the counters and you select that page as the victim that has the smallest value, because the counter, it hasn't incremented and been replaced when it's not referenced. And so you have to search through the page table if you need to. Another one is a so-called stack implementation. So you keep a stack of page numbers, and this stack takes form as a doubly linked list. And every time a page is referenced, you cut it out of where it is in the stack and you move it to the top. And this requires you to change a couple pointer values in order to implement it. And that's big O of 1, so it's very feasible. But this update is more expensive each time you need to make this update. But the good news is there's no search for the replacement, because that page that you're going to replace always is at the top of the stack in that top of stack order. And so this least recently used and optimal are both cases of so-called stack algorithms, and these do not exhibit Belady's anomaly. And so here's an example of using a stack approach. We have our stack, and the top of stack is 2, followed by 1, 0, 7, 4. And we're going to mark this period of time as A, and then we have this reference for page 7, and then we have this point in time B. And so the first stack on the left, that's the stack at that point in time marked by A, and the second stack here is the version of that same stack as a result of that reference to page 7, which is that point in time we're marking by B. And so here we have 7 as our reference. And so if you're going to have 7th as our reference, we're going to take 7 out, and we're going to cut it out of the stack where it is, and then we're going to put it up at top. And so the 7 is at the top of stack, and if we look at the least recently used, well, the most recently used for reference is 7, but the least recently used is down here. And so with the stack-based approach, we can always know which is the least recently used, or the one that has been used the longest period of time ago into the past. There are some approximations to least recently used. LRU needs special hardware, and it can be a bit slow. And so we have a reference bit, and each page is associated with a reference bit, and it's initially equal to 0. Whenever a page is referenced, we go ahead and we set that bit to 1. And so when you're going to make a replacement decision, you replace any page that has a reference bit of 0 if one exists. But the problem then is you also don't know the order in which those pages were referenced. There's another approximation to LRU called the second chance algorithm. And generally, it looks like a FIFO page replacement approach, but you have hardware provided for a reference bit, and then there's also something called clock replacement. Now, with this clock replacement, sometimes it's called second chance. And this second chance clock replacement acts like FIFO, but if a page needs to be replaced, well, if its reference bit is 0, it goes ahead and replaces it. But if its reference bit is 1, meaning that the page was recently referenced, then it goes ahead and sets it to 0, leaves it alone, and gives it a second chance, and goes to the next page in the queue, in FIFO order, to replace it. And so the reason for this is that if it was very recently changed, then it might be accessed for the first time, and it might be subsequently accessed again in the near future. And so the second chance or clock page replacement algorithm looks like the following, and this is in the book. You have a circular queue of pages, and then you have associated with each page, you have a reference bit. So here we have the next victim we're going to select, and if that victim is 1, it sets it to 0 and moves to the next one. It sees that the next one is 1, it sets it to 0 and moves to the next one. And it comes to a 0, so it goes ahead and it replaces that page, selects it as the victim. And so there's also a so-called enhanced second chance algorithm. It operates just like the clock or the second chance algorithm, but it uses a reference bit as well as a modification bit. And so it presents these bits as an ordered pair, starting with the reference bit and the modified bit. And so there are 4 different states for this ordered pair. You can have 0, 0, 0, 1, 1, 0, and 1, 1. If it's 0, 0, that means that it has not been referenced and has not been modified. So it's neither recently been used and it's not been modified. And this is the best page to replace, where the reference bit and modified bit are both 0. Likewise, it could be 0, 1. That means it has not recently been used, but it has been modified at some point in the past. This is not quite as good because when you replace a page with these bits set as 0, 1, you're going to have to write it out before you replace it because it's dirty. It's just been modified. And then we have 1, 0. That means it's recently been used, but it's clean, meaning it has not been modified. So probably it'll be used again soon. It's not as good as 0, 0, but you probably want to leave this one alone or not prefer that one. And then lastly, it's recently been used and been modified. It'll probably be used again soon. And moreover, if you're replacing it, you need to write it out to the backing store or swap space area before you replace it. And so when page replacement is to be performed, using the clock scheme, you use these 4 different categorizations of pages based on these bits to decide what order you consider pages when you're going to replace them. So you might need to search the circular queue many, many times, but you can at least have a finer grained categorization and better control over the decisions your page replacement algorithm is going to make. And so another approach is a so-called counting algorithm. You keep a counter of the number of references that you make to each page, and that's not as common, but with this, another approach is the least frequently used. So that says you replace a page that has the smallest count, and because it has the smallest count, it's not being referenced enough. And if it's not being referenced very much, then you're probably safe to select it as a victim to swap out. Another one's called the most frequently used. Now, this is the different argument that says, okay, well, if a page has a small count, it probably hasn't been accessed a lot, but it will be in the future. If you've accessed the page a lot, well, you're probably almost done with it or done with it completely, so you're not going to access it much more in the future. And so this most frequently used selects as a victim the page with the largest count. And so there are all sorts of takes and variations on these page replacement algorithms. And so you can also buffer pages to kind of keep pages around so that when it comes time to allocate frames to pages, you're not at a loss. And so one of the things that can happen is you keep a pool of free frames always. Keep them on hand so that when it comes time to allocate pages to frames, you have them available when you need them. And you're not trying to find them when you get the page fault. And so in doing so, you read the page into a free frame, and then you still, even though you have a pool of them, select a victim to evict, but that newly freed up frame from evicting a victim, that frame gets added to a pool of freely available frames. Also, you can kind of do a little garbage collection. When it's convenient, just evict a victim, not necessarily when you need to select a page or when you get a page reference. So you can also sit in the background and just garbage collect all of these frames and keep them handy in a pool of free frames so that you always don't defer that decision of eviction always until when you need to assign a page to a frame. You could also possibly keep a list of modified pages and make the opportunity that when the backing store is idle, the disk is not doing anything, you have some daemon that wakes up and just writes those modified pages to the backing store and then set their dirty bits to be non-dirty, set it to 0. Now, in doing so, that means you're regularly purging pages, sending page contents in frames out to the backing store, and so that you don't have to wait to when the fault happens, the page fault happens, to actually do this one at a time. You could possibly keep free frame contents intact and note what's in them, so effectively reusing those frames. So if you reference something before it's reused, then there's no need to load the contents again. You just reuse the existing content if you know you used it before, and then you have a reference to it again. You say, aha, I recognize that particular page. That's process one's page. I have that frame over here. Let me just go ahead and reuse that because I was going to load that page back to where it used to be. And so this is generally useful to reduce the penalty if the wrong victim is selected. You can reuse that frame and just turn on its valid bit and don't have to physically do the loading of the page from the backing store from swap to the frame because the frame has already been populated. So you're reusing the existing contents that before was there before you did the swap, but you don't reload it with something else. You just turn it back on again instead of swapping that same evicted page back in to a new frame. Okay, applications and page replacement. All of these algorithms involve the OS in making an informed judgment or even just a guess about future page access. Now, for some applications, such as databases, they're very complex. They traffic in a lot of data, and they know exactly how they're going to use memory. They're memory intensive, and these memory intensive applications can cause double buffering. Why is this? Well, the operating system keeps pages in memory as it's buffering for I/O from the device buffers, and then the application itself also keeps pages in memory for its own work. And so when you have a device buffer to transfer from a disk for a database into memory, well, the database application keeps it in memory, but it's also in a buffer maintained by the operating system. So this leads to double buffering. So sometimes in some systems, the operating system gives direct access to the disk called raw access and gets out of the way of the application so that the database, for example, can interact with the paging system on its own. And so this bypasses all the buffering and locking, and it can give you much, much better efficiency in the application performance, because who better to tell you how to use pages than the database itself that's using that data. Okay, so with that, that's all I had for today. So we will end here. Again, please make sure you're staying on top of these key milestones. And as usual, please stay healthy, stay safe, and I will see you all on Tuesday.